Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Well, today we want to continue our lecture to the third session. The title of the third session is about the volume of solid revolution in Cartesian coordinate by using this method. In bahasa Indonesia it is called metode cakram. As we see in the third topic, we would like to discuss about the volume of solid revolution with respect to x-axis or with respect to y-axis. I think there are two kinds. The first one is this method and the second one is shell method. Today we want to discuss about the volume of solid revolution with this method or metode cakram. First of all, as a motivation of the solid revolution mean in bahasa Indonesia benda putar. We want to motivate ourselves the solid revolution in Cartesian coordinate is just by giving a standard example like sphere, cylinders, and also cone. You see here the cylinder is actually a solid revolution because we can find the cylinder by using the area, the perpendicular area, and we rotate to one of the axis, maybe x-axis or y-axis. And the cone is also a solid revolution that can be obtained by using a triangle and rotate the triangle surrounding the x-axis or the y-axis. Then we get the cone. Here also the ellipse, the parabole, hyperbole, and so on. It is also a kind of solid revolution. The function of two variable z is equal to x square plus y square. Y square is look like this. It is also solid revolution. Here also, if the area A, we rotate one round surrounding the x revolution, then we get something like this. Then we get the shape of the solid revolution on the right side pictures. We also something like this. If we have the area restricted by x is equal to 0 until x equal to 1, the y-axis, and also the curve y is equal to the square of the x. If we rotate one round surrounding the x-axis, then you get the solid revolution as we saw in the right side pictures, and so on. This is also the area between two curves on above. It is restricted by y is equal to x, and the below is restricted by using y is equal to x square. If this r is rotated one round surrounding the x-axis, then we get the solid revolution as we saw in the right side picture. Here also many pictures like circle. If you rotate one round surrounding the x-axis, then we get this solid revolution. This is actually the cardioid. In polar coordinate, if we rotate one round surrounding the x-axis, then we get a shape like this. This is also a solid revolution. This is also solid revolution. So there are many examples in reality that the solid revolution can be obtained by using a certain area and then rotated one round surrounding the x or the y axis. In mathematics, we always use the symbol something like this. This is the horizontal line is called the x-axis, and the vertical line is called the y-axis. And if we have the area, and then we rotate one round surrounding the, for instance, the maybe y-axis, then we get the solid revolution like in the right side picture. So let us start to discuss how to find the formula of the volume of solid revolution. If we are given the area something like this, it is called R. For instance, if the R is the area, the x comma y, where the x between a and b, and the y between 0 and fx, this is actually this area, and then this area is rotated one round surrounding the x-axis, then we have the solid revolution like this. The problem is that what is the volume of this shape of the solid revolution? We will use the concept of definite integral to describe the formula. How can we get the formula? First of all, we assume that we have assumed that the function f is continuous and non-negative on interval AB. So the area D, that is the area under the curve y is equal to fx, above the x-axis, and the x between x is equal to a until x is equal to b. And then we rotate one round, that means 360 degree or 2 phi, surrounding the x-axis. And then for computing the volume of the solid revolution, we will use it's called rumus volume tabung. Okay, we just use the volume tabung with radius r and the height t, that is equal to the area VR square times the height t, so VR square t. That is the base of the formula to find the formula of the volume of the solid revolution by using this formula. Okay. Because we want to use the concept of definite integral, then we have to use the partition. We take an arbitrary partition P, x0, x1 until xn. This is actually the partition of the interval AB. And then in every subinterval xi minus 1 xi, as the base of the square with high FTI, with TI lies between, or TI is located between xi minus 1 xi. If the square, I mean the square of the partition is rotated surrounding the x-axis, then we have the cylinder. Tabung in English, I think it is cylinder. Then we have a cylinder with the radius is equal to the height, that is FTI, and then the height itself is equal to the delta xi. Delta xi is equal to xi minus 1. Because of that, the element volume is equal to V phi r squared t, where the r is replaced by FTI, so that the element volume is equal to the phi times FTI squared times delta xi. How many element volume we have? Of course, we have n element volumes, n something like this, from I is equal to 1 until n. If we sum up them together, then we have SPF. That is the element volume. So the sigma of the element volume from I is equal to 1 until n, this is actually the SPF, the sum of the partition depending on the function f and the TI. If we take this limit, actually the limit is taken by using the norm p tend to 0. If the norm p tend to 0, it implies that the n tend to infinite. If n tend to infinite, then by the concept of definite integral, it is equal to the phi integral, definite integral, ap fx squared dx. So by using the concept of definite integral, we have that the volume of the solid revolution Vox is equal to the phi integral ap y square dx, where the y is equal to fx. So we get this formula. By the same way, if the D is the area xy such that the y is between C and D, and the x is between 0 and gy, where the gy is the function with respect to y, then by using the same argument, we can prove that the volume of solid revolution, that is rotated one round surrounding the y-axis, is equal to the phi integral CD gy squared dy. Here the integration with respect to y, not with respect to x. Okay. Of course, by using the same argument, if the D, the area of the D lies between f1 and f2. f1 is the above function and f2x is the above function and the f1x is the below function. So if the D is the area between these two functions and the x between A and B, then the volume of the solid revolution between these two curves is equal to the phi integral AB f2 x squared minus f1 x squared. Why? Because the f2 is the above function, and the f1 if the below function. By using the same way, if we have the t is the area between the right side function, the g to x, the left function, the g1x, then the VOY, that is the volume of solid revolution, rotated with respect to y axis, then we get the formula phi integral CD g2y square minus g1y square. I'm sorry, it is false. It is actually g1y. This is g2y. I'm sorry, it is not true. It is false. It must be g1y. This is g2y. So we have all the formula. For example, if we have the function y is equal to the square of the x, that is actually that curve, and then we want to count from x is equal to 0 until x is equal to 4, this area is actually this area, and this area is rotated one round surrounding the x-axis, then we have the shape of the solid revolution like this picture. So how much of the volume of the VOX? By using the previous formula that we found, the VOX is equal to the V integral from 0 until 4. The A is 0 and the B is 4, and the Fx is square, the root square of the x square dx. So this is equal to the phi integral 0 until 4 of the x dx. It's very easy to calculate. The conclusion is that the VOX is equal to the 8 times phi unit volumes. This is the simplest example of our topics. And in the example number A, we rotate this region surrounding the x-axis. What about on the other hand, if we rotate this area not to the x-axis but to the y-axis, and the answer is number B. So the VOY is actually equal. If we have y is equal to x square, then the x is equal to y square. Then the x is equal to the g, or the Fy is equal to y square. So that the volume of the solid revolution obtained by using rotation, one round rotation surrounding the y-axis is the phi integral 0 until 2 of this function. Why this function? Because the y is equal to the root of the x, so that the y square is equal to x. So x square is equal to y square. So y square square, or y quadrat again dy. So altogether the phi integral 0 until 2 of the y power 4, this is equal to phi divided by 5 y power 5 between 0 and 2. We put the 0 to this y and the 2 to this y. We got 32 pi divided by 5 unit volumes. If you ask me why the bound of the integration is 0 and 2, because the integration with respect to 2, because the integration with respect to y, not with respect to x. And from the picture here, if here is 0, here is 4, then here the square of 4 is equal to 2. So the integration not between 0 and 4, but between 0 and the square of 4, that is 2 here. That's why the integration is from 0 until 2. Okay. The second example, we want to find the volume of the solid revolution enclosed above by y is equal to the square, the root square of the 4 minus x square, and the below is equal, y is equal to 0. It is actually the x-axis. It is very easy to calculate, because actually the y is equal to the square of 4 minus x square. It is actually the equation of half circle. I mean, if we have this circle, half circle means only above x-axis from here to here. This is the square. So the volume of the solid revolution that we obtain by using half circle rotated one round surrounding the x-axis is just the Vox is the phi, the integral between the here minus 2 here 2, between minus 2 until 2 of the y square dx, where the y is equal to this one. So the y square is equal to 4 minus x square. We can calculate very easily here, and we got 32 phi divided by 3. And here is actually the volume of the ball with radius 2. There are many books that describe many example, many formula, many exercise beside our lecture notes. For instance, in the book of Ulrich and Roth in 2012, they describe about the circle like this, and from this circle we can describe the volume of the sphere, because actually the sphere is actually the solid revolution that obtained by using the area of the circle rotated one round surrounding the x-axis. I don't want to do it in detail, but I want to show that in many other books we can also find many examples and also exercise. I just want to show you. Here also, if we want to find the solid revolution bounded by the circle, this is actually the circle x square plus y square is equal to 6 square. 6 square is equal to 36. But we restricted from 0 until 4. I mean, the area restricted by the area of the circle from x is equal to 0 until x is equal to 4, not until x is equal to 6, because this circle have radius 6. 6 come from the square root of the 36. So we don't want to calculate all, but only from the x is equal to 0 until x is equal to 4. How can we do that? It's very easy by using our formula. So we restricted the area from x is equal to 0 until x is equal to 4 as in the shaded area. Okay? So the volume is the following. The integral from 0 to 4, not from 0 to 5 to 6, because if you take this from 0 to 6, then you get the volume of the ball, the whole ball. But here is not the whole ball, but it is only a part of the ball. So we have that the volume V is actually the integral from 0 until 4 of the 5y square. What is the y square? Y square is actually equal to 36 minus x square. So that the integral become the 5 times 36 minus x square. We just calculate this expression by using definite integral. It's very easy, and you get 368 phi divided by 3 cubic units atau volume units. The other example is about the ellipse. For example, if we want to calculate the volume of the ellipsoid of revolution, what does ellipsoid mean? Actually, the ellipsoid is a solid revolution obtained by using ellipse rotated with an axis, maybe an x-axis or maybe an y-axis. Okay, so we can calculate by the following way. From the calculus 1, we have the general ellipse equation is the x square divided by a square plus y square divided by b square is equal to 1, or it is equivalent to this expression, and then you have that the y, if you see here the y square is the b square divided by a square times a square minus x square. Why we look for the expression of y square? Because the volume of the solid revolution is using the y square. So the volume of ellipsoid is calculated by using the volume of solid revolution. Okay, let us define the volume of the ellipsoid. Okay, we can only count from the first quadrant, that is from 0 until a, and then the 0 until a, it is only half of the ellipsoid. So the v, the volume of the ellipsoid itself is the 2 times of this integral. So we can only calculate one half of the ellipsoid, not from the other quadrant, but only the first quadrant, and then times 2, because from the first quadrant then the integration between 0 and this point in expression between 0 and a. By using the formula of the volume of the solid revolution, the half of the volume is equal to the integral from 0 until a of the phi y squared dx, or the v is equal to the 2 phi integral 0 until a square of the y square dx. But the y square from the equation of the ellipse, we get this one. So we replace the y square by using the right side, this one, so that we have y square is equal to the b square divided by a square times a square minus x square. It is very easy to calculate by using the definite integral, very easy. Just simple manipulation, and you have the volume is 4 divided by 3 times phi times a times b square cubic unit. This is the volume of the ellipsoid with equation x square divided by a square plus y square divided by b square is equal to 1. I think this is also another example. I don't want to describe it in detail because in the previous example we have similar quadratic equation like this. This is also similar to the previous example. This is also similar to the previous example. Maybe this example is a little bit different. But we will see, if we have the sin x, the y is equal to sin x like this, but we take from the 0 until to the phi, so we have this area in the first quadrant. If the area in the first quadrant restricted by the x-axis, x from 0 until phi, and the above is restricted by the y is equal to sin x, so we have this area. And if this area is rotated one round surrounding the x-axis, then we have the solid resolution like this. What is the volume? The volume is very easy. So the volume is equal to the integral from 0 until phi of the phi y square dx. Since the y is equal to sin x, then we replace the y square is sin square x. And by using very simple calculation of the definite integral, we get the volume is equal to the phi square divided by 2 cubic units. So this solid revolution is very beautiful formula, has a very beautiful formula for the volume is equal to phi square divided by 2 units. Another example coming from the book of Sullivan in chapter 6. I suggest all of the students can see in the book of Sullivan and Miranda in chapter 6 there are many applications of integral over there. I don't want to describe it in detail, of course, because it is already done in our examples. What I want to say is just to show you the variation of the book describe about the application of integral, especially the solid revolution. Yeah, here also the description of the solid revolution in the book of Sullivan. The picture is very impressive, how to prove that and so on. The formula of course are the same, and so on and so on. I don't want to describe it in detail. I just want to give you some example and also some problem that make trigger for you in our discussion and our online discussion. I think that's all that I want to say. This exercise are too many exercises. Maybe we can take some of them to be discussed in our online lecture. I think that's all that I want to say, that I want to describe about the volume of solid revolution by using this method. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.